Alright guys, welcome back. Today we're going to look at a concept known as molar mass. If you can kind of tell from the name what we're going to be talking about today. It's the mass of 1 mole of a given substance. So I can determine the molar mass of a substance given a chemical formula. It's an important idea. We have to know what the chemical formula of that substance is to be able to determine this. So let's take a quick look back at what we were looking at last time, and that was the concept of a mole. We showed last time that you would need 6 million trillion things to have a mole of something. We obviously are going to abbreviate this down into scientific notation just because we don't want to write these zeros, and we know that 6.02 things is going to be equal to 1 mole. So if I have 6.02 times 10 to the 23rd pennies, I have a mole of pennies. If I have 6.02 times 10 to the 23rd atoms, I have a mole of atoms. This is an important concept to have because this number is huge. So it really only applies to things that are very, very, very tiny, like atoms or protons or neutrons. We also talked about the idea that given the idea that neutrons and protons have a mass of 1 atomic mass unit, we've defined an atomic mass unit as the approximate weight of a proton or neutron. They're not the same, but for what we're doing here, they're close enough. They have a mass of 1 atomic mass unit, and from what Avogadro kind of hypothesized using the idea of hydrogen 1, the isotope, we know that if we have 6.02 times 10 to the 23rd AMUs, or 6.02 times 10 to the 23rd protons or neutrons, we have 1 gram of stuff, okay, whatever that might be. So we can now relate the number of protons and neutrons we have, or the number of atoms, really, at that point, to the mass of the substance that we're measuring. So let's take a look at this hydrogen 1 example again, just to make sure we kind of got this squared away. We know that there is 1 proton and no neutrons in this substance, so we know that it has a mass of 1 atomic mass unit. Each one, proton weighs 1, neutron weighs 1, but I only have 1 proton. I know that for every AMU, or if I had a mole of these, I would have 6.02 times 10 to the 23rd AMUs, because I would have a mole of this substance. If that was true, this thing must weigh 1 gram. And we're saying this is per mole, or per Avogadro number, so we know that the mass must be 1 grams per mole. If I have something like hydrogen 2, or deuterium, we change the picture, because now we still have 1 proton, because it's hydrogen, but now we have an extra mass number here, so we have to add an extra neutron. If I have 1 neutron and 1 proton, and they each weigh 1 atomic mass unit, this thing must weigh 2 AMUs. Now let's assume I have a mole of that, 6.02 times 10 to the 23rd of them. That means I have 2 times this amount of mass, which means I'm going to have 2 grams per every mole of substance that I have, or 2 moles of deuterium. I could play this game one more time for tritium. Tritium has 3 protons and neutrons, so it's going to have 3 AMUs, so this one is going to weigh 3 grams per mole. Now these are the 3 naturally occurring isotopes for hydrogen. They all have a different mass. So what on earth, why is it when I go to a periodic table, this is what I see? I see hydrogen with this number with a fraction after it. Well, if you'll remember back to the first units here, this number represents what we call the atomic mass. This is the average mass of the naturally occurring isotopes for that element. These are the 3 naturally occurring isotopes. So to get this number, what we have to do is take the masses of each one. Go ahead and get rid of these. And we have to do a weighted average based on the abundance that they have in the universe. So for these 3 substances, it turns out that 99.1% of all hydrogen is hydrogen 1. About another 0.8% represents hydrogen 2, and that leaves a whole 0.1% for hydrogen 3. So if I want to do a weighted average, and I know that this one weighs 1 gram per mole, this one weighs 2 grams per mole, and this one weighs 3 grams per mole. So if I do my weighted average, 0.991 times 1 gram per mole plus 0.008 times 2 grams per mole plus 0.001 times 3 grams per mole, okay, we're going to get 1.008 grams per mole, or that number that we happen to have on the periodic table. This number is much more useful because when we're doing stuff in lab, we don't have just one of these. We have the naturally occurring abundance of each. So if I have a sample of water, 0.1% of the H's in that water are going to be tritium, and 99.1% of those H's are going to be our normal hydrogen atom. So from now on, we're not going to really focus on the isotopes, but we're going to go on the averaging here. So we're going to go to what is being reported on the periodic table. So that's important that, so we're making that distinguishation. We're moving away from a single atom model here, and we're looking at a mini atoms. Well, and we have to do that because atoms are so small, we never deal with just one. So I've got my hydrogen atom, and we know that this 0.001.008 represents the mass of hydrogen in grams per mole, which means for every 1 mole of hydrogen that I have, I know that it's going to weigh 008 grams. That's huge. That's big, because now I can relate a grouping of hydrogen atoms to the mass that they weigh. And I know that for every 1 mole of H, I also know that I have 6.02 times 10 to the 23rd atoms. I can now count atoms. I can count atoms by weighing them through the relationship of the mole. We can do this for a number of elements on the periodic table. For instance, carbon, a particularly important one. I know that carbon has a mass of 12.001 grams per mole. That means for every 1 mole of carbon I have, it will weigh 12.001 grams, and 12.001 grams of carbon will give me 1.2 times 10 to the 23rd atoms of carbon. So if I wanted to know how many atoms I had in a given amount of carbon, I now have a ratio that I can use. So let's take a look. Let's do an example real quick just to make sure that we're following along with that idea. So I'm going to leave carbon up here so we have a reference. Imagine that I have 6.00 grams of carbon. How many atoms of carbon would I have? Well, I could simply set up a ratio knowing that for every 12.001 grams of carbon I have 1 mole of carbon. That's going to tell me that I have about 0.5 moles of carbon. Now, that wasn't the original question I had asked. I originally wanted to know how many atoms of carbon I had. So I could then take my 0.5 moles of carbon, and knowing that for every 1 mole of carbon I would have 6.02 times 10 to the 23rd atoms of carbon, I know that I'm going to have roughly, again, I'm going to end up writing a little bit low here, 1.2 times 10 to the 22nd atoms of carbon. So by using this simple ratio, we can now connect the microscopic world of atoms to the macroscopic world of scales, and indirectly measure how many atoms I have without ever counting them. Now, what do I do if I have more than just an element? It's pretty rare that we're dealing with just hydrogen or just carbon. So we also have to be ready to deal with things like compounds. So let's say I have something like our good friend H2O. H2O is made of hydrogen, which we've already seen, and a little bit of oxygen. Now, finding out the mass per mole for water is really simple if you know the parts. So I know that for each hydrogen I know it's going to weigh 1.008 grams per mole. But I have to account for the fact that there are 2 of them, okay, per unit. I also know that for every oxygen I have, it's going to weigh 15.999 grams per mole, and I have 1 of those. If I do the math, you end up with about 18 grams per mole. That means for every mole of water, for every 6.02 times 10 to the 23rd H2O molecules I have of, it will weigh 18 grams. That is a huge tool in allowing me to calculate or keep track of molecules and atoms. So before we end our video tonight, I would like to get one last little definition in. So let's make sure let's get a definition for molar mass. Molar mass, let's define it as the mass of 1 mole of a substance in grams.